Right now, as you lie there, something is passing through you. Not a few particles, billions of them every second, streaming through your body, through your bed, through the floor, through the entire planet beneath you, and out the other side without slowing down. They do not touch you. They do not warm you. They leave no trace of any kind. And yet, if our best measurements are correct, they outweigh every atom in the universe by more than 5 to 1. We call it dark matter. And that name is an admission rather than a description. It is not dark in the sense of being black or shadowed. It is dark in the sense that light has no relationship with it at all. It does not shine. It does not glow. It does not absorb, reflect, scatter, or block a single photon. You could pile it in front of a star and see nothing. The only thing it does is pull, and it pulls so hard and across such enormous scales that without it, galaxies would fly apart, clusters would scatter, and the universe we live in could never have assembled itself in the first place. Everything you have ever seen through a telescope is riding on a scaffolding made of something we have never held, never identified, and never directly detected. Tonight, we go looking for it. Not to solve it because nobody has, but to understand exactly how we know that most of the universe is something we cannot see. If you find peace in the deep, unanswered questions of the cosmos, consider subscribing to the channel. Let the quiet mysteries of the universe carry your mind somewhere restful as we drift together through the dark. Welcome aboard, astronaut. Tonight, we drift through the cosmos. We leave Earth behind and rise out of the plane of the Milky Way until the spiral spreads out below us. 400 billion stars turning slowly, arms wound in soft curves, dust lanes threading through the light. It looks complete. It looks like the whole object, but we are only seeing the part that glows. If we could somehow perceive mass instead of light, this galaxy would change shape entirely. The bright spiral would become a small, dense knot at the center of something enormous, a vast, invisible, roughly spherical cloud, stretching outward 10 times further than any star, holding perhaps 5 or 6 times more mass than everything luminous combined. The galaxy, you know, is the small, bright thing at the middle of the galaxy that actually exists. Tonight, we will trace how we discovered this. We will meet the astronomer who first noticed something was wrong in 1933 and was ignored for 40 years. We will follow the measurements that finally made it undeniable. Watch 2 galaxy clusters collide in a way that separated the visible from the invisible, and find the fingerprint of dark matter written into the oldest light in existence. Then we will look at what it might actually be, why 40 years of searching have found nothing, and whether the whole idea might be wrong. Settle in. Let your breathing slow. We are going to spend tonight studying something nobody has ever seen. Let us begin with the accounting. When cosmologists add up everything in the universe, the result is genuinely humbling. Around 5% of the total is ordinary matter. Every star, every planet, every cloud of gas, every rock, every living thing, every atom in your body, all of it together is 5%. About 27% is dark matter, something that has mass and gravity, but no interaction with light. The remaining 68% is dark energy, which is not matter at all. It is whatever is causing the expansion of the universe to accelerate, and it is a separate mystery for another night. If we set dark energy aside and look only at matter, the ratio becomes even starker. Of everything in the universe that has mass, about 85% is dark. Ordinary matter, the kind that makes stars and worlds and people, is the minority component. This is worth sitting with for a moment. Every discovery in the history of astronomy, every planet, every star, every galaxy, every nebula ever photographed belongs to a thin, luminous residue floating on top of something else entirely. We did not begin with this idea. Nobody wanted it. It was forced on us gradually and reluctantly by measurements that refused to make sense any other way. Now, let's go deeper and start where the trouble began. In 1933, a Swiss astronomer named Fritz Zwicky was studying the Coma cluster, an enormous swarm of more than 1,000 galaxies bound together by gravity, several 100 million light-years away. He wanted to weigh it, and there are two ways to do that. The first is simple. Count the galaxies, estimate the stars in each, and add up the mass you can see. The second uses motion. In any gravitationally bound system, the speeds of the members depend on the total mass holding them. Objects in a heavy system move fast because strong gravity is required to keep them from escaping. Objects in a light system move slowly. Zwicky measured the speeds of the galaxies in Coma and calculated the mass required to keep them bound. The two answers did not agree. They were not close. The motions demanded far more mass than the visible galaxies could possibly supply. By his estimate, the cluster needed something like 400 times more matter than he could see. By every visible measure, the Coma cluster should have flown apart long ago. The galaxies were moving too fast to stay together, and yet there they were, still gathered. Zwicky proposed that some unseen material must be holding it. He called it dunkel materie, dark matter. And then the astronomical community largely set the result aside for 4 decades. The measurement was difficult, the man was abrasive, and the conclusion was absurd. But what happens when the same problem appears somewhere much closer to home? In the 1970s, an American astronomer named Vera Rubin, working with instrument builder Kent Ford, began measuring how galaxies rotate. The technique was elegant. Point a spectrograph at a spiral galaxy and study different parts of the disk. On the side rotating toward us, light shifts slightly blue. On the side rotating away, slightly red. From those shifts, you can determine how fast the material at each radius is moving. Everyone knew what the answer should look like. The solar system is the model. Mercury orbits the sun at about 47 kilometers per second. Earth manages 30. Neptune crawls at 5. The pattern is clear, and it comes directly from the fact that nearly all the mass sits at the center. The further out you go, the weaker the pull, the slower you orbit. A spiral galaxy concentrates most of its visible light in the middle, so the outer stars should behave like Neptune, orbiting slowly, falling behind, dragging along at the edge. Rubin measured Andromeda first, then dozens of other spirals. The curves came back wrong every time. The outer stars were not slowing down. They were moving just as fast as the inner ones. The rotation speed rose from the center and then simply flattened, staying nearly constant out to the very edge of the visible disk and beyond. It was not a subtle discrepancy. It was the same result in galaxy after galaxy, and it did not go away. And yet, There's more to this story, because it is worth understanding exactly why that result is impossible. Gravity in an orbit is a balance. The pull inward must exactly match what is needed to keep an object curving around a circle rather than flying off straight. Work that balance out, and it tells you something specific. If essentially all the mass sits inside your orbit, then your speed must fall as you move further out. This is not a theory or a model. It is arithmetic, and it has been confirmed to extraordinary precision within our own solar system. So a flat rotation curve carries exactly one meaning. As you move outward, more mass keeps being enclosed. Every time you increase your distance from the center, the amount of material inside your orbit increases enough to compensate. But the light does not do that. Beyond a certain radius, a spiral galaxy's visible brightness drops away sharply. There are very few stars out there. So the mass must be something that is not producing light. And it cannot be a small correction sitting near the center. It has to extend far outward, well past the visible edge, growing steadily with radius. That is the shape of a halo, a vast, roughly spherical distribution of invisible material in which the bright spiral disk is embedded like a coin dropped into a swimming pool. Rubin's measurements were repeated by other teams on other instruments on hundreds of galaxies. The result held. What had been one eccentric claim about a distant cluster became a universal property of galaxies. The journey continues to a completely independent way of weighing things. Gravity does not only pull on matter, it bends the path of light. Mass curves the space around it, and light traveling through curved space follows a curved route. Put enough mass between us and a distant object, and the intervening mass behaves like a lens. The effects are unmistakable. Distant galaxies behind a massive cluster appear stretched into long, thin arcs smeared around the cluster center. When the alignment is nearly perfect, the background galaxy is drawn out into a complete circle, an Einstein ring. Sometimes a single distant object appears in several places at once, its light having taken multiple routes around the same mass. None of this depends on assumptions about how the intervening object moves, or what it is made of, or whether it is in equilibrium. The amount of bending depends purely on how much mass is there and how it is distributed, so astronomers can weigh a galaxy cluster from the distortion of the galaxies behind it, without ever knowing what the cluster contains. The answer comes back the same. Clusters weigh 5 or 6 times more than their visible contents. There is a subtler version too. Most background galaxies are not dramatically distorted, only very slightly stretched by an amount far too small to see individually. But by measuring the shapes of many thousands and looking for a statistical alignment, astronomers can map the invisible mass across large regions of sky. Those maps show a structure, not scattered blobs, but a connected web of invisible material, with galaxies sitting inside its densest knots. Now, let's go deeper into the single most persuasive piece of evidence we have. In 2006, astronomers published observations of 2 galaxy clusters that had collided head-on, roughly 3.5 billion light-years away. It became known as the Bullet Cluster, and it works as an experiment we could never have designed. Consider what a cluster contains. There are galaxies, which are tiny compared to the distances between them. There is hot gas filling the space between galaxies. which actually accounts for most of the ordinary matter. And if the theory is right, there is dark matter. Now collide two of them, and each component behaves differently. The galaxies pass through because they are small and widely separated, and almost nothing hits anything. The hot gas cannot pass through. Gas collides with gas. It shocks, heats, and slows down. The two gas clouds pile up in the middle and stay there. Dark matter, if it exists and does not interact, should sail straight through like the galaxies. So astronomers measured the collision two ways. X-ray telescopes located the hot gas, which is where most of the ordinary matter is. Gravitational lensing located the mass, wherever it happened to be. The two did not match. The gas sat in the middle, exactly as expected. But the mass measured by lensing had continued onward with the galaxies, split into two clumps on either side. The bulk of the mass was not where the bulk of the ordinary matter was. They had been physically separated by the collision, and we could see both in the same image in different places. But what happens when we look at the oldest evidence of all? The cosmic microwave background is the light released about 380,000 years after the beginning, when the universe finally cooled enough to become transparent. It fills the sky, and it carries faint temperature variations of about 1 part in 100,000. Those variations are frozen sound waves. Before the universe became transparent, matter and radiation were locked together as a single fluid, and gravity and pressure fought each other in oscillations that rippled through it. Here is why dark matter matters enormously. Ordinary matter was coupled to radiation. So when gravity pulled it into a dense region, radiation pressure pushed it back out. It could not simply collapse. Dark matter felt no such resistance. It ignores radiation completely. So while ordinary matter was bouncing in and out, dark matter was quietly sinking into gravitational wells and staying there. That difference shows up in the pattern. When cosmologists analyze the temperature variations by size, they find a series of peaks of fundamental and its overtones. The relative heights of those peaks depend directly on how much ordinary matter and how much dark matter were present. The measurements are extraordinarily precise, and they require both. Remove the dark matter from the calculation, and the predicted pattern does not resemble the observed sky at all. This is completely independent of rotation curves, of lensing, of cluster dynamics, different physics, different era, different instruments. Same answer. And yet, there's more to this story, because dark matter is also the reason anything exists at all. Consider the timing problem. The early universe was almost perfectly smooth, with density variations of about 1 part in 100,000. Today, it contains galaxies, which are roughly 1 million times denser than average. Gravity had to amplify those tiny ripples enormously, and it had about 13 billion years to do it. Run that calculation using only ordinary matter, and it fails badly. The reason is the same coupling problem. Until the universe became transparent, ordinary matter could not begin collapsing because radiation pressure kept pushing it apart. Its structures were repeatedly smoothed out. It only got to start building after 380,000 years. That is not enough time. Simulations that include only ordinary matter produce a universe far too smooth, thin gas, scattered clumps, nothing resembling the galaxies we see. But dark matter, had a head start. Free of radiation pressure, it began collapsing much earlier, quietly assembling a network of gravitational wells throughout the cosmos, while ordinary matter was still trapped in the glowing fog. When the fog finally cleared, ordinary matter found that the structure was already built. It fell into wells that were waiting for it, pooled at the bottom, cooled, and formed stars. Galaxies did not create their dark matter halos. The halos came first, and the galaxies formed inside them. Every star that has ever shone owes its existence to a scaffolding of something we cannot detect. The journey continues, and now we should ask what dark matter is not. The most natural first guess is that it is simply ordinary matter that happens to be dim. Cold gas, dust, dead stars, rogue planets, black holes, things made of atoms that do not shine brightly. Each of these has been checked, and each fails. Gas and dust are ruled out immediately. Both interact with light. Gas glows at characteristic wavelengths, and dust absorbs starlight and re-radiates it as infrared heat. We would see it. Dark matter does neither. Compact dark objects, dead stars, stray planets, small black holes were taken seriously for years. Astronomers searched for them using a clever trick. If such an object passes in front of a distant star, its gravity briefly focuses the light and the star temporarily brightens. Surveys monitored millions of stars for years, looking for those brief brightenings. They found a few, nowhere near enough. Compact objects can account for only a small fraction of the missing mass. There is a deeper constraint too. The abundances of the lightest elements formed in the first minutes after the Big Bang depend sensitively on how many ordinary particles were present. Those abundances have been measured, and they set a firm limit on the total amount of ordinary matter in the universe. That limit is roughly the 5% we already see. There is no room for large quantities of hidden atoms. Whatever dark matter is, it is not made of the same things we are. But that's not all, because there is one candidate we know for certain exists, and it still does not work. Neutrinos. They are real. They are everywhere. They have a small amount of mass, and they barely interact with anything. Trillions pass through you every second from the sun alone. On paper, they look like exactly the sort of thing we are looking for. They fail for two reasons. The first is simply quantity. Cosmological measurements place tight upper limits on the total mass of all the neutrinos in the universe, and it falls far short. They contribute a small fraction of a percent. Not nothing, but nowhere near enough. The second reason is more interesting, and it shapes the entire theory. Neutrinos are extremely light. So in the early universe, they moved at very nearly the speed of light. Physicists call fast-moving dark matter hot, and hot dark matter has a fatal problem. Particles racing across the cosmos do not stay put in small, dense regions. They stream straight out of them, smearing out any small clump before it can grow. A universe dominated by hot dark matter would form only the largest structures first, enormous sheets and superclusters, which would later fragment into smaller pieces. Structure would build from the top down. That is the opposite of what we observe. Deep surveys show small galaxies appearing early and merging into larger ones over time. Structure built from the bottom up. For that to work, the dark matter must have been moving slowly when structure began. Cold, in the language of the field. It is why our standard model of cosmology carries the phrase cold dark matter in its name. Now, let's go deeper into a beautiful consequence that is often overlooked. Why is dark matter arranged in a vast sphere when ordinary matter settles into a thin, elegant disk? The answer reveals something fundamental about it. When a cloud of ordinary gas collapses under gravity, the particles collide. They bump into each other constantly, and those collisions convert orderly motion into heat. The heat radiates away as light, carrying energy out of the system. That is the crucial step. By shedding energy, gas can sink deeper, settle further, and flatten. Rotation prevents it from collapsing along one axis, so the result is a disk, which is why spiral galaxies, planetary systems, and Saturn's rings all share the same flat geometry. Dark matter cannot do any of this. It does not collide with itself in any meaningful way. It does not emit light. It has no mechanism whatsoever for getting rid of energy. So when a dark matter cloud collapses, the particles fall inward, swing through the center, and rise out the other side, keeping all the energy they started with. They orbit forever on long, randomly oriented paths, and the cloud settles into a puffy, roughly spherical swarm. It cannot cool. It cannot flatten. It cannot clump into small, dense objects, which means there are no dark matter planets, no dark matter stars, no dark matter worlds hidden alongside ours. It simply cannot condense that way. The shape of a dark matter halo is not an assumption. It is a direct consequence of something that cannot lose energy. But what happens when we look at how much of it is right here? The Milky Way sits inside a halo that extends outward perhaps 1,000,000 light years, containing something like 1,000,000,000,000 times the mass of the Sun. Our entire visible galaxy is a small bright thing at its center, and that halo passes through the solar system, through Earth, through this room. The estimated local density is very low by everyday standards. Roughly 1 proton's worth of mass in every few cubic centimeters. Across the volume of a human body, the total amount of dark matter present at any moment is utterly negligible. But it is moving. The Sun orbits the galactic center at around 230 kilometers per second, so we are constantly plowing through the halo, and dark matter particles stream through us at hundreds of kilometers per second. Depending on the particle mass assumed, billions of them pass through your body every second. None of them do anything. They do not collide with your atoms. They do not deposit energy. They do not warm you or damage anything. They pass through the entire Earth as though it were not there, because as far as they are concerned, it very nearly is not. There is something quietly extraordinary in that image, astronaut. The most abundant form of matter in the universe is flowing through you right now, in enormous quantities, in perfect silence, and you will never feel a single one of them. There is one more detail worth knowing. Because the Sun is orbiting the galaxy and Earth is orbiting the Sun, our speed through the halo changes slightly across the year. For part of the year, we move with the flow, and for part of it, we move against it. That should produce a tiny annual rise and fall in the rate at which particles strike a detector, peaking around the same date every June. Several experiments have searched for that seasonal rhythm. One has reported seeing it for decades, and no other detector has been able to reproduce the result. It remains one of the longest-running unresolved disagreements in the field. And yet, there's more to this story. So, what could it actually be? Physicists have proposed many possibilities, and a few have dominated the search. The leading candidate for decades was a class of hypothetical particles that are heavy, stable, and interact only through gravity and the weak nuclear force. That combination is appealing because of a striking coincidence. If such particles existed with roughly the mass and interaction strength that certain extensions of particle physics predict, the amount left over from the early universe would be almost exactly the amount of dark matter we observe. That numerical agreement was so suggestive, it earned a nickname among physicists, and it drove an enormous experimental effort. A second candidate is a much lighter particle, originally proposed to solve an unrelated puzzle in the theory of the strong nuclear force. It would be extraordinarily light and extraordinarily numerous, behaving less like a swarm of particles and more like a field filling all of space. Interest in it has grown steadily as other options have narrowed. A third possibility is a heavier, more reclusive cousin of the neutrino, interacting even more weakly than the neutrinos we already know. And there are more exotic ideas. Black holes formed in the first instance after the Big Bang, before any stars existed. Entire families of particles in a hidden sector with their own forces barely connected to ours. The honest position is that we do not know. We have a well-measured phenomenon and a long list of candidates. Now, let's go deeper into 40 years of finding nothing. The search has taken three main forms. The first is direct detection. Build an extremely sensitive detector, place it deep underground where cosmic rays cannot reach, cool it, shield it, and wait for a dark matter particle to strike an atomic nucleus and produce a tiny flash or a faint pulse of charge. These experiments are triumphs of engineering. The largest use several tons of liquid xenon, kilometers below the surface, in laboratories built inside mines and mountains. They can detect a handful of atoms recoiling per year. They have detected nothing. Every experiment has returned a null result, and each one pushes the possible interaction strength lower. The second approach is indirect detection. If dark matter particles occasionally annihilate when they meet, the products would be ordinary particles and gamma rays. Telescopes have searched the galactic center and nearby dwarf galaxies for that signature. There have been intriguing hints. None have survived scrutiny. The third is production. Try to make dark matter in a particle collider by smashing protons together and looking for events where energy and momentum vanish. Nothing conclusive has appeared. There is even a looming limit. As detectors improve, they will eventually become sensitive enough to see neutrinos from the sun and from cosmic rays, which produce an almost identical signal. Beyond that point, distinguishing dark matter from the neutrino background becomes extremely difficult. 40 years of increasingly sophisticated searching has produced increasingly precise statements about what dark matter is not. And yet, there's more to this story. Because while the particle hunters wait, the astronomers have been quietly drawing maps. The weak lensing technique has grown into something remarkable. If you can measure the shapes of enough distant galaxies and detect the tiny statistical stretching imposed by everything between them and us, you can reconstruct where the invisible mass sits. One galaxy tells you nothing. The distortion is far smaller than the galaxy's own natural shape. But average over millions, and the random shapes cancel, while the alignment survives. Large surveys have now done exactly this across enormous areas of sky, producing genuine maps of the dark universe. Not diagrams or artistic impressions, measurements, great filaments and clumps of unseen mass with the visible galaxies sitting inside them like lights strung along a frame. A space telescope launched recently is extending this to a third of the entire sky, measuring billions of galaxies to build a three-dimensional map of how dark matter has been distributed across the last 10 billion years. A new observatory in Chile will photograph the entire southern sky every few nights for a decade, watching the structure change. These surveys have also produced a mild puzzle of their own. The universe they measure appears very slightly smoother and slightly less clumped than the oldest light predicts it should be by now. The disagreement is small, and it may yet dissolve into some subtlety of measurement. But it is being watched carefully, because if it holds, it would mean something in our picture of how structure grows is not quite right. But what happens if the whole idea is wrong? It is a fair question, and it deserves a fair answer. The evidence for dark matter is entirely gravitational. Every observation says the same thing. Gravity is stronger than the visible matter can explain. There are two ways to read that. Either there is extra matter, or our law of gravity is incomplete on large scales. In 1983, a physicist proposed the second option. The idea was that below a certain very small acceleration, gravity behaves slightly differently than the standard equations predict, falling off more gently than expected. It is not a wild proposal, and it works remarkably well in one specific domain. With a single adjustable constant, it reproduces the rotation curves of a wide range of galaxies with impressive accuracy, including some cases where the dark matter picture requires careful fitting. It also explains a tight observed relationship between how fast a galaxy rotates and how much light it emits, which remains somewhat awkward for the standard picture. But it struggles badly elsewhere. It does not correctly describe galaxy clusters without adding some unseen mass anyway. It has difficulty with the cosmic microwave background, where the peak heights require an actual substance that does not interact with radiation. And it has real trouble with the bullet cluster, where the mass is physically separated from the visible matter. If gravity simply worked differently, the extra pull should stay where the matter is. Most physicists therefore favor dark matter as a substance. But the alternative continues to be developed, and the galaxy-scale successes remain a genuine puzzle that the standard picture has to explain. And yet, there's more to this story, and it comes from a strange place. Galaxies that have almost no dark matter at all. In 2018, astronomers reported a faint, diffuse galaxy whose star motions indicated almost no unseen mass. Its visible stars alone appeared to account for essentially everything. A second similar galaxy was found nearby soon after. The results were controversial, and the distance measurements were disputed for years because distance strongly affects the inferred mass. But the findings have largely held up. At first glance, this looks like a problem for dark matter. In fact, it is one of the better arguments for it. Think about what the alternative theory claims. If galaxy rotation is caused by a modification to gravity itself, then every galaxy must obey it. A law of nature cannot be switched off in particular galaxies. Any object with that much visible matter at those accelerations would have to show the extra pull. But if dark matter is a substance, it can be removed. A galaxy that passed close to a much larger neighbor could have had its loosely bound halo stripped away by tidal forces while its tightly bound stars stayed put. Both of these galaxies sit near a large elliptical, exactly where such stripping would be expected. Substances can be separated from other substances. Laws of physics cannot be locally suspended. The galaxies with no dark matter may be the clearest sign that dark matter is a thing rather than a mistake. The journey continues, one last time, to the problems that remain. The standard picture works beautifully on large scales. Simulations that include cold dark matter reproduce the cosmic web, the distribution of clusters, and the statistics of galaxies with remarkable accuracy. On small scales, the agreement is less comfortable. Simulations predict that dark matter should pile up into a sharp, dense spike at the center of every galaxy. Many observed galaxies, particularly small ones, instead show a flatter, gentler central region. The two shapes do not match, and the discrepancy has resisted easy resolution for decades. Simulations also predict that large galaxies should be surrounded by enormous numbers of small satellite halos, each potentially hosting a dwarf galaxy. We observe far fewer than predicted, though improved surveys have steadily found more faint ones and narrowed the gap. There are possible explanations. Exploding stars and outflows from young galaxies could push dark matter around and smooth out central spikes. Many small halos may simply have failed to form stars at all, leaving them genuinely invisible. Or the properties of dark matter may differ from what the simplest models assume. None of this threatens the core evidence. Rotation curves, lensing, the bullet cluster, the cosmic microwave background, and structure formation all point the same direction with overwhelming consistency. But it does mean the picture is unfinished. We know dark matter is there, and roughly how much and roughly how it is arranged. We do not know what it is, and the details still disagree with us in places. Take a quiet moment to reflect on what this means, astronaut. There is a version of this story that sounds like failure. 40 years of searching, enormous detectors buried under mountains, thousands of physicists, and no particle found. But look at what we actually accomplished. We weighed things we cannot see, using the motion of stars and the bending of light and the temperature of an ancient glow and the arrangement of galaxies across billions of light years. 5 completely independent methods, drawing on different physics and different eras of cosmic history, all converging on the same number. We did not detect dark matter. We proved it is there anyway, with a precision that would have seemed impossible a century ago. And there is something worth appreciating in the position we are in. The universe still has a genuine, unsolved mystery in it, sitting at the very center of our best theories, weighing 5 times more than everything familiar. We are not living at the end of physics. We are living in the middle of it, with the largest question still open. Most of the universe remains unknown to us. Not unknown in some vague, poetic sense, but specifically, measurably, quantifiably unknown. 85% of the matter in existence is something we have never identified. And somehow, out of that thin, luminous 5%, something assembled itself that could notice the discrepancy. we drift homeward now, back down through the invisible halo we never left, back toward the small bright disk of stars we call home. Nothing about the view has changed. The Milky Way still turns exactly as it always did, its arms glowing softly, its dust lanes dark against the light. The scaffolding holding it together remains completely invisible, exactly as it has been for 13 billion years. Below you, Earth turns quietly, and the halo streams through it without noticing, as it always has. There is no urgency here. The particles will keep passing through you tonight, whether you think about them or not. Somewhere under a mountain, a detector is waiting patiently in the dark, and it will still be waiting in the morning. Close your eyes now. Let the unanswered questions rest where they are. Not everything needs solving tonight. Mission complete, astronaut. The stars will wait for you. Good night.